In this module, we will talk about the determination of KLA values by gassing out technique. What is gassing out technique? As concerned the gassing out technique for the estimation of KLA, it depends upon the monitoring of increase in the dissolved oxygen in a solution during aeration and agitation, during the fermentation process. The oxygen transfer rate, OTR, will decrease during the period of aeration as Cl approaches to C star. Due to the decline in the driving force, C star to Cl, the oxygen transfer rate at any time will equal to the slope of the slope of the tangent to the curve of the volume values of the dissolved oxygen concentration. This whole link we will discuss in detail in next slide. Just see on this slide that x-axis is the time. Here is the dissolved oxygen concentration. So the increase in the dissolved oxygen concentration of a solution over a period of aeration. So when we just increase the aeration, then the dissolved oxygen will go out, and then there will be a constant, and this point is known as the critical. So the oxygen transfer rate at x is equal to the slope of the tangent at y. So this y is the slope of the tangent at point 8. To monitor the increase in dissolved oxygen over the adequate range, it is necessary to first decrease the oxygen level to very low. Two methods are mostly utilized for the estimation of gassing out technique. One is the static method and other is the dynamic method. So in later slides we will see what is the static method and what is the dynamic method by which we can reduce the dissolved oxygen concentration into a very low values up to 0. So these are two techniques. One is static. So the static method of gassing out, in this technique the oxygen concentration is lowered down by gassing the liquid with another gas. Mostly the nitrogen gas is used. The whole medium has to sparger with the nitrogen gas, by which the oxygen in the medium replaced by the nitrogen gas. So the solution is scrubbed free from oxygen. So the deoxygenated liquid is then aerated, and with the proper agitation, then the increase in the dissolved oxygen concentration will be monitored using any probe, which we called as a dissolved oxygen probe. The relationship of the increased dissolved oxygen concentration can be described by this equation. dCl over dt is equal to KLA into C star minus Cl. If we just integrate this equation just to calculate, then there will be a ln log of nature of C star minus Cl. C star minus Cl is actually the driving force, is equal to minus KLA and T. So if we plot the graph between T and the L and H, then the slope of that graph will be minus KLA. So just by Lineweaver-Burke plot, we can calculate the volumetric mass transfer coefficient by this equation. So you can see in this that how we can use this equation just to calculate the slope of this will be the minus KLA. So by this chart we can minus sign show this kind of the graph. This method is acceptable for only the small scale of fermentation, because when we have to gassing out with the nitrogen, excess nitrogen is utilized. That increase the cost of the production. But on a large scale fermentation, this method of which we called as static method of gassing out is not recommended, because that is very difficult to sparger the large fermenter with the nitrogen that can reduce and that can scrum the oxygen from the medium completely. So then there is an alternative way, that is just an other methods which we talk about, the dynamic methods. So when the air supply to a such vessel is resumed after deoxygenated with the nitrogen, the oxygen concentration in the gas phase may change with the time. So the nitrogen is replaced with the air, thus the C star will no longer be constant. So this is the limitation of this static method, but on a large scale fermentation, this is another option which we will talk about and discuss in our next module.